Alright, silly people, here's the situation. The next project Mark Newman is going to have us work on in VPython is a model of the solar system in motion around the sun, right? Um, with all of the planets pretty much to scale with each other, and all of the orbits pretty much in scale, right? And so he gave us the data on a few of the planets in the book. I'm just going to use that data and then scale it. I did do this before, and so I know and played around with it quite a bit, so I know what scaling options I like. So, of course, we have to start with importing VPython. So import VPython as VP, and also I'm going to need NumPy for some of the planetary motion. The first thing that I did was I made a really big VPython canvas, uh, so I could actually see everything. So I had it width equal to 1000, height also equal to, or let's just do height equals 800, so it'll actually show up on the OBS. And then, so I just created all of the objects that were given in the problem statement first, and then created a for loop and then updated the positions as the for loop was going, right? So first of all, we need the sun. It's going to be a sphere, and it's going to be at the position 0, 0, 0. So 0, 0, 0. It's going to be in the center of the whole thing. And then this is something that is optional, but I made it so that I downloaded a bunch of like observatory data and NASA data to get surface maps of each of the planets, and then just named each of them whatever planetary body they are .jpg. So I'm using the texture argument to get those maps onto the spheres, and then I'm gonna type in the radius of the sun. I think this is in kilometers or thousands of kilometers, something like that, but it's 695,500 according to Mark Newman. But then I scaled it by dividing it by 5e to the 4, so that it actually all shows up, right? And then going in the order of what is closest to the sun to what is furthest from it, we're going to do Mercury, Venus, Earth, Mars, Jupiter, and Saturn, right? Saturn. They're all going to be vp.sphere objects, so I'm just going to take this equal sign here, copy it, and stick it on all of these planetary objects, and then try to make it so that the equal signs are at the same horizontal position because OCD reasons. And then I'm going to have all of them have a position argument, a texture argument, and a radius argument, right? So I'm also going to copy down those and then type in a bunch of numbers for those. So copy, then paste, 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 paste. So, and I don't know why I'm doing it like this, but all of the positions have to be vp.vector objects. So let me get a bunch of those as well. vp.vector. And then bam, 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 bam. Okay. Now, so the first thing is Mercury, right? According to Mark Newman, it's 57.900 away from the sun. That's its radius, and so I'm just making that its x position. So I'm basically starting with theta equals 0 for all these. So for Mercury, it was 108.20. For Earth, it was 149.60. And then make sure to follow those up with 0, 0, because those are just going to be the x positions, right? Mars, it was 227.90. And then for Jupiter, it was 778.50. And then the furthest guy from the sun was Saturn with 1433.4, right? I'm going to put in the textures. So there's going to be mercury.jpg, and then this will be venus.jpg, and earth.jpg, and mars.jpg, and jupiter.jpg. This is getting, I mean, it's a little bit tedious, but it's going to be cool. Saturn.jpg, and then, yeah, just gonna move these guys also that the radius is at the same starting point. Okay. Then typing in the radii of each planet, I'm gonna do Mercury first with 2,440. For each of these, I ended up scaling them down by 1,000. So divide by 1,000, and then Venus was 6052, and then divide that by 1,000. Earth was 6371, divide that by 1,000, and then this is 3386 divided by 1,000, and then Jupiter, big boy, 69,173. Divide that by 1,000, and then Saturn was 57,316. Then divide that by 1,000. Cool. So now all of those objects should exist within our VPython canvas. The next thing is to actually start animating it. So I'm going to create a for loop that's going to iterate over values of theta in a NumPy A range, which is going to go from 0 to something with a lot of zeros. So 1, 0, 0, 0, 0, 0, 0, 0 was what I found worked, incremented by 0.1. That's just so the program will run for approximately ever. It won't ever stop, realistically. And then you have to declare a frame rate. I used a frame rate of 300. This just means that for every second, the theta is going to iterate up by 0.1 300 times, right? That's what I've got working on my machine. And then for each of these, we actually have to now update the positions. So we've got a bunch of planets.pos to change the position. Each of them is going to be a new VPython vector. And I'm going to type out all the names of the planets again. Venus, actually spell it correctly, Earth, Mars, Jupiter, Saturn, and then take this piece of shit right here and copy it down to each of these lines So to get the new positions, you just want to take like the conversion from polar coordinates to Cartesian coordinates. So you want the x to be r cosine theta and the y to be r sine theta, and we're going to keep everything in the same plane, so all the z values are going to be 0. So 0, 0, 0, 0, 0, 0. But then all these are going to be quite different. So the x value for Mercury, the radius of its orbit was, again, 57.9. And then you multiply that by cosine of theta. And then I ended up dividing each of the thetas within the trig functions by the planet's period. I thought that was a good way to try and scale like the relative periods to each planet specifically. It might be not the best way. That's how I did it. I kind of liked how it looked. But yeah, I'm just dividing it by 88 since that's how many days it takes Mercury to orbit Earth, right? But then you have to put in the y value as well. So that's going to be 57.900 times n numpy sine function of theta divided by 88.000, right? And then actually one more zeros on each of those 88s. It's going to make it look real nice. Okay, for Venus, it was 108.20, and then you multiply by cosine theta. And then Venus orbits the Earth every 224.7 days, right? And so that's x, then y will be 108.2 times numpy sine of theta divided by 224.700. Right? Yeah. Make everything look great in the code. Earth was 249.60, and then this is going to be multiplied by cosine theta. Of course, everybody knows that the Earth orbits the Sun in 365.3 days. And I wish I could actually type the number 3. And then this is going to be 149.60 times sine theta, 365.3. Okay, Mars is looking like 227.90 times cosine of theta divided by, and then the period of Mars was 687 days. It's a long year. Would not want to live on Mars. 227.90 times sine theta 687.000. Got it. And then finally Jupiter is 778.5. Then pi cosine theta. And then Jupiter's period is 4,331.6 days, right? And then we got 778.7 times sine theta divided by 4,331.60. And then Saturn is looking like 433.4 times cosine theta divided by, and then The period of Saturn is the longest. It's 100. It's 10,759.2 days in a year. Right, and then this is 1433.4 times sine theta over 107.59.2. Right. Okay. With that, I think it should run. So let's give that a go. And then I hope it actually shows up. Yeah, let me just move it in here. So you can kind of move around the window. So I'm going to zoom in a little bit. So there's the sun in the center with a little Mercury orbiting around. Notice that Mercury is orbiting quite a bit faster than Venus, which is orbiting quite a bit faster than Earth. There's Earth. Whee! Then zoom out a bit and you'll find little Mars here, also orbiting the sun a little bit slower than Earth. And then you gotta kind of pan over here to see the big boys, Jupiter and Saturn. You can see that they are very slightly moving with respect to the background, at least. It's just very, very slow compared to all of the dirt planets that are over there just spinning away, having a whale of a time. Didn't make Saturn's rings, but that's okay. That's kind of too much work. It couldn't be asked. But yeah, solar system. I invite you to play around with this. Try and find, settings that work for you better. Maybe make the simulation a little bit more physically robust. But this is pretty cool to me. All right.